Hi everybody. In today's video, we will be solving a problem on Nyquist theorem. So this is the problem. A signal g of t, which is 10 cos 20 pi t cos 200 pi t, is sampled at 250 samples per second. There are three parts of this problem. The first part is draw the spectrum of the resultant sampling signal. Second is specify the cutoff frequency of the ideal filter so as to recover g of t at the receiver side. And third part is what is the Nyquist rate of g of t. So we have to solve these three problems. So before I solve this, let me just give a quick recap on the Fourier transform. So let me go to the last page here where I have just written a quick recap. So this is we'll just talk about what is Fourier transform of what is called as complex exponential. So complex exponential is a signal of this format: e power j 2 pi f naught t. Basically, it's a sinusoidal signal with equal in phase as well as quadrature phase component and frequency f naught. So the Fourier transform of a quadrature of a complex exponential signal is del of f minus f naught. So if you have to derive it, it's pretty simple derivation. You just take a Fourier inverse of this and you will directly get e power j 2 pi f naught t. So pretty straightforward derivation of Fourier transform of a complex exponential. So now if we take a signal cos 2 pi f naught t, we all know from Euler's theorem cos 2 pi f naught t is e power j 2 pi f naught t plus e power minus j 2 pi f naught t by 2. So just substituting this formula, we get Fourier transform of cos 2 pi f naught t is 1 by 2. Fourier transform of e power j 2 pi f naught t is del of f minus f naught, as we discussed here. And Fourier transform of e power minus j 2 pi f naught t is del of f plus f naught. So the Fourier transform of cos 2 pi f naught t is 1 by 2 into del of 1 by 2 times del of f minus f naught plus del of f plus f naught. Similarly, the Fourier transform of sine f naught t would be 1 by 2j times del of f minus f naught minus of del of f plus f naught, since sine 2 pi f naught t is e power j 2 pi f naught t minus e power minus j 2 pi f naught t by 2j. So we will use these two formulas in our problem solving. So let's go back to our problem. So first part of the problem is spectrum of the resultant sampling signal. When we say spectrum of a signal, it just means the frequency domain representation of that signal. So our signal is g of t is 10 cos 20 pi t cos 200 pi t. Now we all know from basic trigonometry cos a cos b is 1 by 2 cos a plus b plus cos a minus b. We all know cos a plus b is cos a cos b minus sin a sin b. Cos a minus b is cos a cos b plus sin a sin b. So if I add these two, I'll get 2 cos a cos b. So if I do 1 by 2, I'll get cos a cos b. So just substitute. This is of the format 10 cos a cos b. Here a is 20 pi and b is 200 pi. So if I just substitute here, I get g of t is 10 into 1 by 2 cos a plus b is 20 pi t plus 200 pi t plus cos a minus b would be 200 pi t minus 20 pi t. So just going on further, that simplifies to 5 cos 220 plus 200 is 220 plus 5 cos 200 minus 20 is 180 pi t. So this is my g of t. Now let me convert into a standard cos 2 pi f naught t format. So it comes to 5 cos. If I take 2 pi common, it comes to 2 pi times 110t plus 5 cos 2 pi times 90t. So this is I just converted it into 2 pi f naught t. Now I know cos 2 pi f naught t is Fourier transform, that is cos of 1 by 2 del of f minus f naught plus del of f plus f naught. So if I just substitute it here, I get 5 into 1 by 2. Here f naught is 110. So del of f minus 110 plus del of f plus 110. Similarly, if I take Fourier transform this part, it comes to 5 by 2 del of f minus 90 plus del of f plus 90. So 5 by 2 is 2 by 5, which I can take as common. So I get 2.5. So g of f would be, so this is the Fourier transform of g of t, which is g of f. So it would come to 2.5 del of f minus 110 plus del of f plus 110 plus del of f minus 90 plus del of f plus 90. So if you have to plot it, you can see the magnitude is 2.5, and there are basically four impulse signals, and my del of f minus 110 is at plus 110, f plus 110 would be at minus 110, del of f minus 90 would be at plus 90, and del of f plus 90 would be minus 90. So there are four impulses with each magnitude of 2.5, and there are four impulses at the 4 points. So that's the spectrum of g of t. Now the question is spectrum of the sample signal. So we all know g del f is, we saw this in last video, is fs times m, summation m from minus infinity to infinity g of f minus mfs. Here the fs is sampling frequency, which is given in the question as 250 samples per second. So if I just substitute this, I would get 250 times summation m minus infinity g of f minus 250 m. So I just expanded it here, but let me just plot it without looking at it. So the magnitude here, so okay, if I substitute it here, you'll get 250. G of f I know is del of f minus 110, so it will be del of 110 minus 250 m, since that's here, plus del of f plus 110 minus 250 m, f minus 90 minus 250 m, del of f plus 90 minus 250 m. But for plotting, I don't have to look into this. If you just see this, when m equal to 0, this is nothing but 250 times g of f. So, and I know g of f is four impulses, one at 110 minus 90, 90 and 110. So when m equal to 0, I get same four impulses at 110 minus 90, 90, 10, and the magnitude would be 250 times g of f, since there is a 250 multiplier here from g of f. So the magnitude will be 250.2.5, which is 625, which is the magnitude. Now when m equal to 1 here, when m is equal to 1, this is g of f minus 250. So everything would be right shifted by 250. So this entire thing would be right shifted by 250. So minus 110 plus 250 is 140. 110 plus 250 is 360. So it will be at four impulses will be at 140, 160, 340, 360. So this entire thing is for m equal to 1. Similarly, when m equal to minus 1, this will left shift by 250. So minus 110 minus 250 is minus 360. 110 minus 260 is minus 140. So this entire thing is for m equal to minus 1, and so on. It continues. So this is the spectrum of the sample signal. Very similar to how the derivation we did. Just that instead of triangle, the spectrum here looks like four impulses. Now the second part of the question. Specify the cutoff frequency of the ideal filter so as to recover g of t. So you can, it's very straightforward. You can see that g of this part is nothing but g of f. So for me to recover g of f, I should reject everything else, just allow these four frequency components to get through, which means my cutoff ideal filter has to be somewhere between 110 and 140. If it's more than 140, this additional spectrum will get in, frequency component will get in. If it is less than 140, I don't get any unnecessary frequency component, but if it is less than 110, I lose some of the required frequency component. So the this cutoff filter has to be, so let me just draw it again, just clean it up a little. So the cutoff filter will have to be something like this, which has to be between 110 and 140. So that's the cutoff frequency for ideal filter, must be between 110 and 140 hertz. And the third part of the problem is, what is the Nyquist rate of GOT? We all know Nyquist rate is 2 times the highest frequency component of the signal. So here the highest frequency component is 110 hertz. So Nyquist rate is 2 into 110 hertz, which is 220 hertz or 220 samples per second. So as we can see in the problem, they want the sampling rate was 250 samples per second. Your Nyquist rate is 220 samples per second. So the sampling rate was greater than Nyquist rate. That's why we could recover the signal using a cutoff frequency. If my sampling rate was less than 220, I would not be able to recover the original signal at the receiver side. So hope you guys found this video useful. We just solved a problem on the Nyquist theorem. Thank you everybody.